Before we actually jump into SolidWorks, I'm going to kind of introduce things with a PowerPoint. And again, my name is Brendan, and first topic for this afternoon is advanced mating techniques. All right, so mates. If you're like me, we've all gotten stressed out from time to time trying to deal with our mates, getting them to work and do what we want. Sometimes we even find our mates fighting with each other. We're going to kind of discuss that and what we should do when this happens. And it'd also be a lot nicer if maybe our mates had a little more intelligence to them. So I'm going to show you some tricks here to add a little more intelligence to our parts. And here's kind of our route or our plan of attack. Okay, and first I'm going to discuss planning. Okay, just like when you go to model a part, you should come up with a plan before getting started. And if you're like me, you get excited, you just want to dive right in. It's a big mistake. Okay, in the case of a part, you pick the wrong place for your origin or the wrong feature to start with, and you end up hosing yourself down the line. So same thing with assemblies. You want to plan them out. Here are a couple things that you should probably think about before starting your assembly. How many instances of this sub-assembly, maybe, or this assembly, are you going to use in the top-level assembly? When you're adding your mates, how can you mimic real-life behavior of the parts, picking the right planes, faces, and things like that to describe the real mechanical behavior. Okay, don't just grab faces because they're there and they make sense at the moment. Think about the mechanism and the way it works. Manufacturing and bill of materials, this drives a lot of our assembly decisions. Are we purchasing this assembly already put together? Are we putting it together in our own shop? Are we putting all the parts together at once, or are we having several people in the shop working on sub-assemblies? Things like that. So you kind of want to drive your assembly choices with those facts. And then again, are you going to reuse this sub-assembly in the future, or does it only exist in this project? And lastly, where should you put your parts? In the sub-assembly or in the top level? And again, manufacturing is probably going to drive that decision for the most part. But if you have a choice, you'll want to use sub-assemblies. Okay, so again, here's some tips. For those parts you are going to reuse a lot, add intelligence to them. Okay, add intelligence to the sub-assemblies, add intelligence to the parts. When you're doing your mates, avoid chains of mates. Do more of a baseline mating scheme. Okay, don't mate part A to part B and then B to C and C to D. Instead, mate B, C, and D all back to A. You'll have a much better time in the future if you go to replace a component or modify components and things like that. You'll end up with less mate errors. Start with your bigger parts first, okay, and work your way down to the smaller, less important parts. Okay, like in the case of this boom, we want to definitely put that that bracket in there first, and then the big pivot arms. But those little plates and hardware and guards and bushings, those things are going to come last. In fact, save hardware for the last. Okay, kind of like in a part, we save fillets for the very end. Save your hardware for the very end. There's no need to put it in early. You're slowing yourself down. And then if you put it in at the end, you kind of avoid that chain of mates issue. Okay, yeah. So again, coming up with a good plan. You'll avoid rework, avoid errors, better organization, especially if there's several people working on this sub-assembly together. Okay, have a plan of attack. Okay, next, mating. So here I'm going to show you all the speed tricks, help you make mates a little bit faster. All right, I'm going to hold Alt and press Tab. That'll let me jump from my PowerPoint right to SolidWorks. Okay, and here I've got several components to put together. Again, I'm going to do more of a baseline scheme and avoid that chain. There's actually a tool in the mate dialog that is specifically for this. Okay, it's also really fast. Again, that button's been here a while, but you probably haven't checked it out before. Multiple mate mode. Okay, all I got to do is select the face on part A, and then I can grab B, C, and D, just one after the other. So I got 3 mates done right away. We can even organize our mate folder a little bit by throwing those into a subfolder. And then my next set of mates, same thing. I'll grab the base components, okay, and then grab the other 2 less important components. Okay, and then we'll just finish this off with one regular mate. All right, next, anytime you have symmetry, try to plan your symmetry out. Okay, we always want to capture symmetry in parts, but same thing with subassemblies. Okay, here I've got my right plane right down the middle of the part. Again, by utilizing symmetry, I can now mirror these components to the other side. So if it makes sense, use the component patterns. Okay, the pattern instances don't need mates, so you're going to have a smaller mate folder, and then any changes you make to the original mating scheme will automatically update the other patterns. Okay, so here we'll go ahead and launch our mirror component pattern. Notice how I pre-selected everything. I think that's a faster option because it puts everything in the right boxes for you. So you can fill out the property manager a lot faster. And next I'm going to use one of the advanced mates to center this object up. Okay, there's no need to do the math to try to figure out a distance mate. We have a centering mate. In fact, we have a lot of advanced mates which help get better mechanical behavior in. And just like I had mentioned, I'm going to pre-select all the faces involved. That way when I do hit the mate commands, it puts them all in the correct boxes for me right away. And if we look over at the left, you'll see there's a lot of advanced mates which can get more complex motion than the standard mates. And then there's even mechanical mates. Again, very helpful to describe real-life mechanical systems. So if one of these mates makes sense, use them instead of the standard mates. And then we'll finish this off with one last concentric mate. You notice my pattern instances are already fully defined, okay, because I put those in first. Or because I use my mirror, sorry. All right, next, I'm going to show you a speed trick to get your mates done faster. Okay, I can hold Alt and drag a face to another face, and it'll automatically add the mates. Okay, and I'm going to hold down my right click on the part so I can rotate to the face that I want to use. Okay, this flat face. So again, I hold Alt, then I hold my left click on the first face, hover over the second face, and they automatically snap. So they call that a quick mate or a smart mate. Okay, and I get this little toolbar in case I want to do a distance mate or a parallel mate instead. Okay, and I get a reverse direction in case it's backwards. But then if I go ahead and hit OK, it actually adds that mate into the mate folder, and I never even had to launch the mate dialog. And again, I can do this to get the rest of the bushing into the hole. I hold Alt, hold my left click, hover over the other face, and he snaps into place. Take a note of the icon next to my cursor. Okay, that's letting me know which mate type it's going to default to. And now I need to let go of the mouse first, and then let go of Alt, and then hit OK. Okay, now you can see that mate's already in position. Now if I hold Control and then click drag this bushing, I can make a copy. Now really I have symmetry here, so what I would normally do is another mirror component. Okay, that would be a smarter idea. I'm going to make a copy and do this again just to show you another trick. This time I'm going to do the same thing I just did, but I'm going to grab the edge instead. Okay, if I hold Alt, grab a circular edge to another circular edge, notice I have a different icon this time. It actually did the concentric and coincident at the same time because I got the circular edge. All right, next I'm going to grab some additional components, but from some other places. They're not in the file yet, or they're not in my assembly yet. Okay, this drag and snap technique can work out of the library. So maybe you have a commonly used part like this grease fitting here. If I drag it from my library into the assembly, notice he wants to snap to different circular edges. Okay, he'll just grab the closest edge to my mouse. So again, I can drag and snap him right into place. All right, a cool advantage here is that I can add several instances of this component into the assembly in case I want more than one grease fitting. All right, next in 2012 we added some additional search tools. You can find those right up here in the upper right, and searching for models has actually been around longer than that, but the other ones are new. And here I'm going to search for this wear plate. Okay, SolidWorks is going to go through all my folders that I've designated to search in. So you would want to point them to all your common part folders. But the cool thing about it is you don't actually need to know the name of the part. Okay, it could be any piece of metadata or any feature name inside the part. Maybe I renamed a feature called wear plate, or maybe the wear plate is just a description of the model. It's not the actual file name. Notice how much stuff came up just because it's related to the word wear or the word plate. Okay, so all of this could be dragged. You don't even need to know what folder it's coming from necessarily. Okay, and if I drag it from my search window into position, notice it automatically wants to snap. Notice I'm getting the wrong orientation though. Before I let go of my mouse, if I press Tab, I can toggle and reverse the direction in case I'm getting it backwards. So there I'm just pressing Tab. Now that it's in the right orientation, I'll let go of my mouse. All right, I need another wear plate at the bottom. And again, normally I would just have a mirror component already done for the bushing, so I would just edit that and include the wear plate. But here I wanted to show you another trick. If I hold Control and Alt at the same time, then drag this edge, I can make a copy and duplicate those mates at the same time. Notice the wear plate down below is already in position. So that's a Control-Alt drag. All right, now I could also pull up Windows Explorer and browse to parts and do the same thing. So you can drag from Windows Explorer into your assembly. Okay, that's great if you have several parts you need to do and they're all saved in the same folder. And now another thing we could do is drag across windows. I'm going to use the new quick tile buttons that came in 2012, and I can get these guys side by side. Okay, so if I drag a face from one, or if I drag my assembly from one window to the other, notice he's automatically wanting to snap and pick up geometry. Okay, just from one window to the next. Okay, now that guy's not in the correct position yet, but a little more work and he will be. So the Alt drag also works with assemblies. And again, I would do a width mate at this point. So again, pre-selecting is the fastest option. Okay, and then we'll hit the make command. All right, and there we've got our knuckle assembly completed and in the top level. Again, I would mirror that to the other side, just like I did before. Now, if I hold Control and then start pressing Tab, I can get to some other open documents, like this mating flange. I'm going to tile them to the other side. Again, we'll drag across windows, and then we'll automatically get some mates to pop up. But there's an extra advantage here because there's a hole pattern. You notice the hole pattern on the yellow flange and then the hole pattern on the gray flange. Because the quantities match up, it knows to add a third mate to align those holes. And if I start pressing Tab, it'll actually clock the flange I'm inserting so I can get, some keyways aligned or something like that. So all I'm doing is pressing Tab and it's going from one hole to the next. Okay, and then I let go. It just added 3 mates for me. Again, a concentric to align the flanges, a concentric to align one of the hole patterns, and then my coincident all at once. So those are some great speed tricks that we have for mating. All right, and now adding intelligence. Okay, like the bushing we just saw. Okay, I didn't run my interference detection, but there was some interference there. And that's because we normally bore out an additional hole, add a fillet or chamfer, something like that, every time we use this bushing. And since I'm going to use this bushing a lot in the future, it's better to add intelligence to it. It'll take more time up front, but in the long run, it's going to save me a ton of time. Okay, there's another piece of intelligence that we can add for assembly, and that's a mate reference. Essentially, you tell the part what mate you're going to use in the future, and then it'll automatically hunt for that mate for you. So we'll take a look at how to add those in. All right, now what you want to do is you want to draw up a dummy part, if you will, or an example part. So this is a part that's not going to be used in production. It's something that I could throw away at the end when I'm done. And you want to do this because it's going to try to establish references from the bushing to this assembly and then ultimately to this dummy part. Okay, so you don't want to do it on your real part at first. Okay, not the setup. And then you'll want to insert your dummy part into your dummy assembly. Now your dummy part should have a similar shape to the real part that you're going to use it on. So like my, my knuckle piece in that assembly was circular and cylindrical in nature. So I drew a cylinder here. Okay, and another piece of intelligence I want to add is the mate reference. So every time I put this bushing into an assembly, I add the concentric mate and I add the coincident mate every time. Well, I can set those up in advance. It's under your reference geometry tool where you've got your planes and axes. You can launch the mate reference. Okay, and in this case, I want to get the circular edge as my primary default mate. That way it'll try to add both concentric and coincident. Okay, now my secondary option might be the concentric, just in case it can't do the primary. And I can even specify the mate type. I know it's never going to be tangent. It's always going to be concentric, so I can force it to that. And then in the event it can't get secondary, we could do tertiary. And here it'll always be coincident. and it'll always be anti-aligned. The last thing I can do here is I could rename this mate reference. But if I do that, it'll only look for other parts that also have a mate reference with the exact same name. I don't want to do that here because I might drop this bushing on a lot of different parts. So I want to leave the name default. But let's say like the flange we saw. I'm always putting the 6-inch flange on another 6-inch flange. Since those two are always going to be going together, I would give them a name, 6-inch flange mate, something like that. So that's what the name is for. So normally you want to leave this at default. Okay, now if I jump back to my assembly and I insert that bushing, or that bearing, the second I get close to the circular edge, he's snapping into place. I do not need to hold Alt or anything. I'm just hovering. If I hover near the bottom edge, he wants to snap down there. So much quicker technique. All those mates are already done. They're in there. Next bit of intelligence is every time I use this bushing, I make that same cut, and I add the same fillet and the same chamfer and the same wear plate. Those features and parts can come along for the ride, so I don't have to insert them every time. All right, and the way you do this is you insert your real part, the part you're actually going to use, and then put it together with the dummy part, and then you edit the dummy part in context. Now, to eliminate unnecessary references, you will want to be careful about how many references you create to the dummy part. Okay, any reference I set up to the dummy part needs to be reconnected in the future part. For instance, I'm going to start a sketch on this face. So in the future, it's not going to know what face to put the sketch on. I'm going to have to tell it. So you want to minimize some of that. Okay, in this case, starting the sketch here is not that bad. Okay, I'm going to throw it in wireframe because I want to copy some information. Now I want to copy or relate as much information to the bushing as I can, because then I won't need to reestablish it. So if I grab this edge and do a offset entities or convert entities, something like that, that's going to come along automatically in the future. And now we'll go ahead and hold down or right click and use our new mouse gesture tool to create an extruded cut. Now I want to go to the bottom of the bushing, but I can't see the bottom. I can get this face out of the way by right clicking and going to, well, first of all, setting my end condition up to surface, and then right clicking the face that's in my way and doing select other. I can continue to right click other faces in the model and get those out of the way. Okay, once I can see the face I want, I'll hover over it and left click. Okay, notice now our cut has intelligence. So that's really important in case I change the size of the bearing in the future, or maybe I have a lot of configurations of the bearing, different sizes. The cut is intelligent. All right, we'll hit OK. All right, next I'm going to go ahead and create a fillet. And we'll create a chamfer. All right, and then we're done editing that component. But I also bring the wear plate along most of the time, or maybe every time. So you should go ahead and insert that now as well. Okay, make sure you add the mates and everything, and try to add the mates to the bushing so later we don't need to reconnect them. All right, now under your Tools menu, down near the bottom, you'll find Make Smart Component. Okay, or you could use our new command search. And then we could type in smart component. Okay, now here you can actually launch the command from this drop-down, or you could hit the eyeglasses to find out where you had put that button. And notice it moves your cursor there and points to it with the red arrow. Okay, it is not on your assembly toolbar by default. You need to customize your toolbar and put it there. Okay, but I'm going to grab my bearing, and he's going to be the smart component. And now the wear plate is going to come along for the ride. So this is great for hardware. And then I'm going to grab all the features that also should come along. You can grab as many features as you'd like. There's even an auto size option in case your bearing does have configurations. It'll know the correct size to use based off the geometry you drop it on. All right, and that's it. Okay, now I need to save all this at least once. But now that I've saved it, I could delete my dummy assembly and my dummy part if I choose. But if you think you're going to edit your choices that you made in the future, you might not want to delete them. You might want to store them in a safe place. Okay? Again, that's up to you. All right, but now let's check it out. In the part, you have the Smart Features folder, okay, where everything is stored. If you right-click it and go to Edit and Defining Assembly, as long as you didn't throw the dummy assembly away, it'll go find it and you could change your decisions. And right here is the mate reference where that is stored. All right, but now I'm going to go ahead and grab that knuckle assembly again. But this time, when I insert my bearing, he's automatically wanting to snap to different, circular holes, as we see. And I place them in there. If we do a quick section view, you'll see I've got that interference at the moment. But if I click on my part to wake up this little star, and then I left-click that star, it's going to ask me to first reconnect the references that are missing. Okay, like I said, we're going to miss our sketch plane, so I need to pick a new sketch plane. The little picture shows you your original choice in the dummy model. So here, this is the face that makes sense to put my new sketch. Next, I can choose which features I want and which components I want. Maybe this time I don't want the wear plate. Okay, I could turn it off. Or maybe I don't want the chamfer this time. I'll turn it off. Okay, now if we look at our section view, okay, you'll see it added the extra cut, and it added the fillet at the bottom, and it added the wear plate. All right, so that's a great way of kind of saving yourself a lot of time for future work. All right, and now our next topic, repairing mates. There's a lot of tools to help you fix your mates faster. Okay, just like errors in a part, errors in an assembly because of mates are not unavoidable, but they're going to happen. Again, it's just natural when we make changes, they happen. But as long as you follow some good techniques to fixing them, it's not going to be so bad. Okay, right here I'm going to use my new 2013 quick filters to find that top level assembly. Notice I didn't need to browse to try to figure out which component's the largest. Okay, I can get right to that top level assembly. Okay, and once this opens up, you'll see I've got errors all over the place in my tree. Now, this is what you don't want to do. Open up your big mates folder and scroll up and down and try to solve your mate problem. Okay, it's way too daunting. I can't really tell how many problems I have. It's difficult to work with because everything's called concentric. Okay, this just isn't the best place to view the issues and work with them. Okay, however, the folder itself has two tools in it which can be helpful. Okay, if you right-click your mates folder and go to what's wrong, okay, a lot of times this message comes up on its own. I kind of get tired of seeing it every time, so I have in the past unchecked these so it doesn't show me every time I hit rebuild what's wrong. And I know some of the descriptions aren't terribly helpful, but there is actually something in here that can be really helpful. Okay, notice a lot of these messages say the mate is over defining the assembly. That tells me it's actually a mate issue. But sometimes a mate issue is really a part issue. It's a geometry issue, not a mate issue. And here's the hint. Okay, anytime the description of the error involves a value, chances are things can't align because of geometry, and it's not a mate problem, but a geometry problem. Okay, and the most common scenario is holes not aligning or bosses not being wide enough for faces to actually be coincident, things like that. So that can give you a hint right there. Oh, another thing I like to point out. The difference between a warning and an error. Okay, all of these mates are fighting with each other. This essentially lets me know who is winning the fight right now. Okay, if a mate has a warning, he's winning. Okay, and he's actually solving, and we're seeing that mate in action. Okay, if a mate has an error, he's losing the fight, and he's kind of given up at the moment. So he is not solving. So that can give you a hint as well. Now, as we saw there, there's about 12, it looks like there's about 12 issues in this assembly, but that's not true. There's 12 errors and warnings, but how many problems actually exist? Okay, the next tool in this right click helps you figure that out. Mate Expert. All you got to do is hit diagnose, and it hunts through all the issues and it figures out how many actual problems there are. And notice, even though I had 12 warnings and errors, there's only 2 problems. Okay, the first problem appears to be a hole alignment issue. Okay, again, I had that hint in the what's wrong. Okay, so I need to check my geometry, and I'll show you a trick there in a second. Quick way to check the geometry on those. And then the second problem seems to be an alignment issue with the boom, okay, and the arm together. So things don't look quite centered like I would expect them to be. So that appears to be a mate issue. And we'll solve that one with another trick. Okay, so now that I know I only have 2 problems and I know where they are, and I can visually see them on the screen, now I can attack them. Okay, there's actually an advanced select tool that can help you with a lot of things, like selecting all your hardware and suppressing it. Okay, again, now I've got a much smaller mate tree. I can work faster, things like that. Okay, so I like to highlight these advanced select tools. A lot of people aren't aware of them. You can even make your own advanced select tools. This one allows you to customize and make your own. Notice I have one that grabs all the small parts. Okay, but another great one is select mated to. Okay, I know one of the issues was with this guard, so I'll give it a left click and then say select mated to. Okay, and then if I hold control and grab the guard again, and then right click and space, and go to isolate. This will temporarily hide everything else out of the way so I can really focus on the issue at hand. Okay, it's really hard to fix mates when you got all the parts in there in the way, especially if I need to measure geometry. All right, so I'm going to pull up my measure tool. Okay, and I'll measure the hole distance here. Okay, it looks like it's giving me the minimum. Okay, well, in recent years, we can now toggle this right here. I'm going to do center to center. And we see my center to center distance is 300. Okay, I click in space and I can do a new measurement. And that's 290. Now, I don't know how many times this has happened to me, but I'm going to pretend I forgot my first measurement. So in the past, I would have to go remeasure the first measurement. Well, new in 2013 is measurement history. So it'll show me other measurements that I made during this SolidWorks session. And right here, right away, I can see my previous measurement was 300. My new one is 290. So that makes sense why my mates are failing. They can't align the holes. So here's a real simple solution. I need to edit either the guard or I need to edit the spacing of those tabs. Here I'm going to edit the dimension of the guard and rebuild. Okay, and now we see the guard's errors have gone away. I'm going to go ahead and undo that. You'll see why. Another quick way of finding the mates for a specific component. You could go to the tree, find the part, find his mate folder. That's pretty easy. But if you actually select a part and then hit the Property Manager tab, notice it gives you a nice short list so you can see just the mates. Okay, if I click on the next part, I can see just his mates. So that's a nice way of truncating your list of mates to only the ones you want to look at. And now this time, when I make this change to 290 and hit rebuild, we'll see those errors go away. Okay, I solved that problem. Okay, and now I could save this display state or exit and get back to all my other parts. I'm going to save it real quick just to show you that next time, all I got to do to get back to those groups of parts is right-click this double arrow and select display state. Right-click it again, go back to the default. So take advantage of display states. All right, next, I can see that this part is off-center. Okay, and really it's this whole subassembly. If you grab something in the tree that has mate errors, go to your context bar and hit View Mates. Okay, this also runs that isolate command and it adds transparency to the other parts involved in the mates. So again, really helping me focus on the problem. Okay, in addition to that, new to 2012, is this gray bar in the middle. It's splitting up the parent and child mates. Everything above the bar is what is putting this assembly into position. Everything below the bar is other parts mating themselves to the subassembly. So by looking at a parent-child list, it might help you determine what mate needs to be deleted, who needs to go. Another cool thing in here is I can grab this mate and I get a little call out highlighting the faces that I used in the selection of that mate. And it gives me options to try out to fix the problem. Okay, and I don't necessarily need to commit to the problem right away. Okay, notice we've got two mates here that are conflicting. coincident 39 as a warning, so I know he is winning the fight right now. Okay, if you grab the one that has the error, this first button with the exclamation point, if I click it, now this mate is winning the fight. Okay, so you can try out the two different mate options this way and visibly see the difference on the screen. If this mate is winning, he's not centered. If this one is winning, he is. So I know which mate I want to suppress now. So notice in there is suppress, flip direction, edit mate, or force to solve. So try out all four of those buttons and eventually you're going to find the right solution. And notice the errors are gone. So now I can go to the next subassembly, go to View Mates, and try the same thing. Click on the one that has the error. Okay, we notice we don't like what we see, but we tell it to force to solve. Now he's winning the fight, and I do like what I see. So I know it's this other one with the error that needs to go away. And notice I've now solved all my issues. This guy doesn't have an error, but he's incorrect as well. So I'll grab him, go to the property manager to see his mates, and without editing them, I can right-click and say flip alignment. And again, view everything to make sure it looks correct, and then I can close it. So there's a handful of tools to help you solve mate issues. Okay, it's still up to you to solve them, but visibly makes things so much easier to work with and actually get to the root of the issue. So that kind of concludes this portion of my demonstration, okay, repairing mates. All right, and now for my corny wrap-up joke. Now that we've got some direction and some new ideas, maybe we'll learn to love our mates. All right, so thanks for attending that one. Give me a second here. I'm going to close. I'm going to go ahead and close all my files down. I'm going to turn on my simulation, and that'll be our next two topics. Okay, and they're actually directly related, so I'm going to go from one to the other. All right, so our first simulation topic here is mesh controls. Okay, I actually have a sub-assembly I want to get open here. And then I'm going to fire up this PowerPoint. Again, just to introduce the topic. All right, so I know some of us might be new to simulation, so I'm going to kind of discuss the basics as well. But I'm going to throw in some advanced tricks along the way for our advanced users. So what are mesh controls? Why do I need them? When do I use them? And split lines, what do those have to do with meshes? Okay, these are all questions that I'm going to answer. Okay, and then for those of us that are new to simulation, simulation is for analysis of the part, setting up a real-life scenario and then testing the part to make sure it's going to function and hold up the way we expect. Okay, there's a lot of different simulations you can run. You can run stress analysis, displacement analysis, drop tests, frequency, buckling, vibration, response, thermal, a whole gambit of simulation tools. And they all work very similar. Basically what we do is we take a model and break it down into thousands, if not millions, of little elements, okay? These little tetrahedral elements. Now when we place them all together, this new element model looks exactly like the original. And then we're essentially running a free body diagram. Okay, we'll set up displacement equations at all the nodes of these elements and then apply fixtures and loads to figure out how far things displace, and then from that we can calculate stress. Okay, now the issue here though is speed versus accuracy. In theory, I would like all of these tetrahedrals to be infinitely small. If I do that, I get the perfect hand calc answer. But it would take years for my computer to solve it. So that's obviously not good. So you got to find this balance of element size and accuracy versus speed and performance. So we want to reduce those elements, but we don't want to reduce them everywhere. And that's what a mesh control is. I want to reduce element size, but only in certain areas where I need the accuracy. Okay, so accuracy is dependent on mesh size. Mesh control is better than global control because I can get more speed that way. I can put them in all the areas that I'm interested in and all the areas where I think I might have error, and then get the accuracy only where I need it. It can also help you with mesh issues if you're having problems getting a mesh to complete. Okay, a mesh control is the answer most of the time. You can also get better contact created. Okay, contact is very dependent on mesh size. And then it's also a way we're going to check for convergence, which is our final topic of the day. All right, all you got to do is right-click your mesh folder here to find the mesh control tool. Okay, but there's even some mesh control options in the default global mesh setup. Okay, we're going to take a look at all of those. So what you do is you grab geometry where you're interested in or where you have quick changes in values, okay, like quick stress gradients or temperature gradients. Okay, pick a new size and then a transition speed or a transition ratio. And again, here's all the benefits. I've kind of said them already, but just wrapping up all the benefits here and the way we use it. Split lines is another topic I'm going to introduce. That can control mesh shape, locations for mesh controls, but really we use it all the time in simulation to control where a load is applied, where a fixture sits. A mesh control or a split line gets me new faces I can grab without editing the geometry or changing the geometry. All right, and so now we'll jump into SolidWorks simulation. And now I've turned simulation on, I have a simulation tool or toolbar. For those of you that don't have a license to simulation, you do still have a smaller version with not as much power, but it's great for a part like this. You know, a simple part. You have Simulation Express. Okay, but I'm going to use the full simulation product. Okay, and everything I'm talking about, both in my mesh control topic and my convergence topic, applies to all the different study types. But I'm going to focus on the static studies. Okay, and we'll give our study a new name. I'm going to call this the default mesh. Okay, and we'll just right-click our mesh folder and go to Create Mesh. And then if I hit OK right away, I get the default mesh. Notice the mesh control actually occurred on its own. Okay, and I'm going to jump back into the default mesh. Okay, and that's because of a certain option that I had turned on. Okay, I'm going to go back to a standard mesh and then even dumb down the size a little bit, make the elements a little bit bigger. Okay, now you see the elements actually map the part pretty well. And we kind of have a rule in simulation. I call it the two-layer rule. You need at least 2 layers of elements across the thin sections of your part. Notice here I have 2 layers, and up here I have 3 layers. So for the most part, this mesh is really good already. However, we also have a 2-layer rule across a 90-degree fillet. And again, it's at least 2 layers. 3 would be ideal. But notice I only have 1 layer, so that's not very good. Okay, in fact, I'm going to go ahead and finish the setup here real quick. Okay, we'll fix the top face, and then we'll apply a load on this lower face. And then I'm going to run the analysis. Okay, the reason I wanted to run it is there's a couple of things that can give you hints as to where you need mesh control. Okay, right away, just looking at the color on the plot, notice how this transitions from the dark blue to the light blue really slowly and smoothly. Okay, that's a good indication that my mesh is already good enough in this area. And it even goes from light blue to kind of a teal to a green, really nice and smooth. So again, here my mesh elements are already a good size. But right here, I have a very quick change in stress values, okay, a stress gradient. Notice it jumps from red to almost green right away. There's no smooth transition there. It looks kind of patchy. That's a good hint as to where I need mesh control. Okay, even down here, kind of internal into the material, same thing. It's a little spotty and splotchy. So I would like to apply a mesh control to this face and then have it bleed down into the material a little bit. Okay. But up here, you know, pretty nice and smooth across the thickness. This is looking not so bad. Okay, there's also a plot for this. Okay, if you right-click your results and go to Define Stress Plot, you have our energy norm error plot. Okay, there's 2 different averaging techniques. No need to get into the details, but in theory, if I made my elements infinitely small, the 2 averaging techniques would give me the exact same result. There would be a 0% difference. But here, again, in those kind of splotchier areas, you're going to tend to see a much higher error. Notice this element has 61% error. And again, that doesn't mean that's the error in my result. That's the difference between my 2 averaging techniques. So quite a big difference. And again, reducing element size is the solution here. So I'm going to duplicate my study. And we'll call this one Mesh Control. The reason I right-click and duplicate my study is so I can compare my new answer versus my previous, okay, without losing results. Okay, and all I got to do is right-click my mesh folder and go to Apply Mesh Control. Okay, and I can grab corners or edges. Or in this case, what I want is a face. If this was an assembly, I could grab an entire body, you know, entire part. Okay, we'll pick a new size for us. And then a transition speed. Okay, I'm going to go with a really quick speed at first. And we'll take a look at that. All right, so I put in a value of 3, which means my elements are going to triple in size or grow by 300% until they get back to the global size. So notice the transition is really fast. I want to slow it down so I can get some smaller elements down here as well. Okay, so I can go find that initial control, right-click it and edit the definition. Let's grow the elements by just 10% each time, each layer. Okay, now you can see that transition speed is nice and slow. So my mesh control kind of bleeds its way to the rest of the model, if you will. And now if I run my study, you can see how much smoother that transition got. It's still pretty quick, but it's looking nice and smooth. And if we were to look at the energy norm error plot, you can see it's gotten a lot better. Now it looks like I might need some mesh controls up top, but if we ignore that up there and just look at the bottom, okay, I got everything down to, between 0 and 10%. So that's pretty good. If you can get everything below 5%, that's awesome. Okay, but if you're in the 0 to 10, or if you're in the 10% range, that's not bad. Okay? So already, I think that mesh control is good enough here. Now I don't want to be. Now I'm not totally confident on that. I need to check for convergence to be sure, but at the moment, I'm thinking that's pretty good. All right, next I'm going to show you some additional options. Here we've got automatic transition. Now, because this face is smaller than my global size, it has to put in a smaller element. Well, I can get an automatic transition speed right here under my mesh parameters, automatic transition. Again, you'll see it had to put smaller elements on the fillet just because of the fillet size, and then you get to see a little bit of a transition. So that right away gives you a little bit of mesh control. Okay, it's not great. It's not as good as the other option we saw, but it's a little bit. Okay, and then next, this is a new great one that I like. It's not that new. It's been around for several years, but curvature-based mesh. It's right here. So the standard mesher, picks a corner of the model, puts an element there, and then it bleeds to the rest of the model. Okay, what curvature-based mesh does is it starts with all the curved faces first. So it's going to do all the fillets, all the holes, all the curves first, and you get to specify a minimum number of elements on a fillet. Okay, now here let's say we did a top size of 6 and a top of 4, and then I want a lot of elements around my fillet, 30. Now that would be 30 around a hole, so this fillet is just going to do 7.5. Okay, actually let's make this 32, so it does 8. It's going to try to put 8 elements around that fillet. Notice I only put 2 or 2.5. Okay, that's because I made my lower bound too high. I need to drop that in order for it to fit 8 elements there. Okay, so you want to pay attention to your lower and upper bounds. And then we can even put in that same transition speed from earlier, 10%. And again, notice I now got my 8 layers of elements, which is a little excessive. And then I've got my really slow transition speed. So it does a very similar thing as the mesh control, except it only does it on curved faces. But a lot of times, it is the fillets and the holes where we have high stress. So if you have a lot of fillets and holes in your model, curvature-based mesher might be the way to go. Okay, and you can use those in combination. I can use mesh controls and curvature-based meshes at the same time. All right, now for an assembly issue. Okay, sometimes it can be really difficult to get an assembly meshed correctly the first time. Okay, especially when we have really large parts like this knuckle or this caliper, and then we have really small parts like these washers and these these alignment rods, or these guides. Okay, so I'm going to go ahead and create a mesh. And, we'll stick with, pretty much the default size, standard mesher here. But what it does, is it picks a size, a global size that makes sense considering the whole volume of the assembly. So it's a relatively big assembly, and so it went with a relatively big size, 15 millimeters. Some of my parts aren't even 15 millimeters in diameter, let alone their thickness. And notice right away I can see I have a failure before the mesh is even done if the knuckle failed. Okay, we'll let it wrap up here. New to 2012, you get the mesh failure diagnostics coming up right away. New to 2013, you get that sound when it's done. Maybe you're checking your email while you're waiting. You'll know when SolidWorks is finished with something. If I go ahead and launch this up, it tells me what parts failed and why. Was it the face? Was it an edge? Okay, I can actually click those faces and edges, and it's highlighting them on the screen. And then it's giving me 3 options to check out. Okay, if you see edge failures in particular, maybe you have a really small feature like a step or a groove or a really tiny fillet or chamfer that you should get rid of. Okay, you should simplify and get rid of some of the details that aren't contributing to the strength of the part. Okay, and that's what it means by check geometry. Open up the knuckle, look the geometry over and make sure you got rid of the small little detail features that you don't want. Incompatible mesh. Okay, this is a bonding option when we have parts bonding together. Notice if I zoom in here to this ear and this washer, the nodes on the neighboring bodies are in alignment. That simplifies the bonding equation, which is helpful for speed. But in a lot of cases, it can cause a mesh failure. So another option is to toggle it to incompatible so the nodes do not need to line up. Okay, it might solve a little bit slower, but at least your mesh works. There's some other reasons you might toggle that as well, which we don't have time to get into. But the third option is a mesh control. And notice it'll automatically throw in the faces for me into the mesh control by selecting them here in the list, so I don't need to find them on the screen. Okay, now I could try giving them a smaller size, a better size, and then I can remesh just the failed part. This is new to 2012 and it's huge. In the past, I would need to remesh everything, which took a little while. So from here on out, you'll want to make sure to just hit the Create Mesh button. It's also warning me that it needs to change that contact option to incompatible for that part only, which is okay. Okay, now with that new mesh control, it was able to get around the original problem. Okay, notice how it only had to remesh the knuckle, so it was really nice and fast. And again, we see how a control can really solve the problem. Now that new enhancement, you do not need to limit yourself to a failure to use it. I can actually come to my parts folder and find some parts, okay, like these, the rod, the nut, the washer, for instance. I can right-click them and say remesh. Okay, it's going to create a mesh control, just like as if I went to the folder myself. I can tell it to use the size it would have used if I was only analyzing these parts, so it goes with a default smaller size, and then I can create a mesh just for them. Okay, so it's fast, it's quick, and it's going to get you more accuracy notice how much better the nut and the washer look compared to the first nut and washer. So I can kind of go through all the small parts in my assembly and get a much better mesh on them faster, way faster than I ever could before. So that's a new enhancement in 2012. All right, and then finally, split lines. Okay, notice it, just do the element size it chose. It has a pretty nice uniform element size, and it's pretty symmetric as well. That's really nice. Sometimes, though, we've got an additional body in contact here. You know, again, maybe we've got an assembly or something like that. So let's pretend this is an additional body pushing on the bracket. Okay, I can say don't merge results, and essentially I've got a multi-body par file, and as far as simulation is concerned, okay, it might as well be an assembly. Okay, I do need to remesh it since I changed some geometry. And if I go ahead and hide this body, I need to refresh my plot. I can do that by hiding the plot and then re-showing the plot. Oh, I must have had a different contact option than I was expecting. Okay, I need to run this mesh one more time. Okay, in the event you have a bonded compatible contact, like the default is, notice how it imprints the face from the other body onto this body. Okay, you can see that oval shape, okay, in the mesh. And again, that helps to ensure good bonding and alignment, that node alignment. It'll solve quickly, it'll bond well. And again, just given my element size, I have some symmetry, but it was just kind of dumb luck. Notice here I do not have symmetry, and I don't really have as many nodes here as I would like. I want to run this one more time, just get the right size. All right, here we go. So yeah, you can see kind of the asymmetrical behavior here. And again, I'm not necessarily getting as many nodes as I would like, things like that. Here's the situation where a split line is your friend. If I jump back into SolidWorks and start a sketch, okay, and I go ahead and just draw a line across the model, there is a split line command which will use a sketch to split one face into two faces. The geometry is the same, but I've got two faces. Now I am forcing nodes to fall on that split line. So even with the exact same settings as before, you will see that I now have symmetry across my model. Now my boss that I drew, I did not center on the model, so that was an issue. But let's say we got this centered up. And then I rerun my mesh. Okay, now I've got a symmetrical mesh result along the area of contact. Okay, and then I can even apply mesh controls to my split line. Okay, again, we can grab lines, edges, or I could grab this face and not that one, something like that. And then rerun my mesh. So again, using split lines to help get symmetry, help getting small elements in only certain areas, It's a great technique. And now convergence, my last topic here. All right. All right, this is just a fun little example of someone not running simulation on their parts, right? We put it out in real life. You know, the parts get stressed, they fracture, maybe they fatigue. Who knows? Again, an assortment of problems I can solve for it. Well, in this case, somebody did run analysis on it, but they failed at validating their study, and they failed at checking for convergence. Okay, you cannot just set up one study, run it, look at the result, and then say, okay, that's correct, and move along. You've got to check for convergence. Okay, and you need to validate your study. And again, just kind of jumping into the basics of FEA. Again, we're going to solve equations at these little red nodes on every element, and that will allow us to figure out the displacements, strains, and stresses in our model, or temperatures, or whatever, again, study we're running. We have several different element types, so when should I use solids? Well, you want solids to be your default choice. Okay, you're going to use solids pretty much every time unless one of these other things is true. Okay, if your parts are really thin, okay, you know, thin plastic parts or sheet metal. Sheet metal is maybe the most common. I got really thin walls. It's going to be impossible to meet your two-layer rule and solve the problem quickly. So that's when you go for the shell element. Now those red nodes now have rotation degrees of freedom. And given the material and the thickness of your part, we know how likely that node is to resist that rotation, and from that we can calculate the stress through the thickness of the part. So the shells are still really accurate. Now you might take a small hit in accuracy, but they're so much faster to run, you'll be able to reduce your element size more, and you make that accuracy right back up, pretty much. So same thing with beams. You know, introducing, we know the cross-section profile of the member, so we can calculate its strength in those two directions. And then introducing new degrees of freedom on the nodes, we can get accurate stress results. So there are your long, slender shapes with constant cross-section profiles. Okay, so frames. Now a lot of times you need to mix and match all of these. Okay, again, classic example is a car. You know, the chassis will use beams, but then all the gussets and other sheet metal will use shells. And then the bigger, bulkier parts, plates and hardware, will use solids. Now, what is convergence? Again, this is the effect of reducing that element size, and we notice the values start to change. But eventually, they stop changing. Okay, that's convergence. And really what we want to do is reduce elements where we need using mesh controls, like we just learned, monitor the results in several locations, and then when we see the results stop changing by 5% or less, we've converged, and you could stop. Now, the reason I say 5%, not 1%, is because you've made a lot of assumptions, you know, simplifications, and those have introduced more than 5% error anyways, so there's no need to reduce the mesh error that much, okay? We'll compensate for that error with factors of safety, right? So now, if we take a look at a manual method of checking for convergence, we'll jump into SolidWorks and look at that. Now, I I had initially set this up on that drive shaft, but just for time's sake, I want to do it on maybe a simpler part. So I do have the drive shaft example. If you guys would like to look at it, just let me know. But I'm going to do it on this classic textbook example we were just working on. And again, we have some study already set up. Again, I should rename this and call it my default mesh, or maybe my initial run, or something like that. Something that makes it unique compared to the other studies. Okay, and we'll solve the problem and get some results. And here's the mistake that a lot of people make. They look at that max value, they compare it to their yield strength, and then they say they passed or they failed and they move on. Bad idea. Let me go ahead and put this in a unit system that I'm a little more familiar with. And we'll also, easier to read, we've got yield strength of 30 KSI, and right now our stress is at 12 KSI. So we passed with a factor of safety of 2.5. Okay, so we can even throw up a factor of safety plot. Okay, well, you'll always want to kind of edit the definition of these a lot of times to truncate the model to what makes a little more sense. I'm even going to throw my mesh onto this plot. Notice how the whole model is red because most of the model is down near the 2.5 to 3% factor of safety. But we've got one element or one node with 0 stress, so it's got a really high factor of safety and it's throwing everything off. Well, if you right-click your plot and go to Chart Options, we can turn off the max, turn on the min, and then we can customize the legend. So it doesn't trim itself to the min and the max. Maybe we want to make the min 0 and the max 5. And notice how that's a lot more helpful to look at. We could even make it our requirement. Maybe our requirement is 2%, is 2, something like that. So I see everything passed. But again, maybe to get a little more distribution of color, we'll make it 10. All right, remember, you've got that other plot called the energy norm error plot. Again, there's 2 averaging techniques to determine those values, and this is showing you the discrepancy between the 2. Now, the default averaging technique is the more accurate one, so you don't need to worry about toggling it. But again, the reason we have 2 is for determining potential error due to mesh. And you can see there's a lot. Big difference. All right, so the way we check for convergence is apply a mesh control and then reduce element size. Okay, so I'll right-click my plot and duplicate it. And we'll call this mesh refinement. Or let's call it convergence checking 1. Okay, we'll apply our mesh control and reduce our element size. And then we'll rerun. Okay, it just went from 12 to 13.6. So you can see it's a fairly decent sized jump. But I got to warn you about this. I just made a mistake. Do not look at the max value on your legend and use that for your convergence checking. Sometimes we get things in simulation called singularities. Okay, you get one element that's just, or one node that doesn't have enough neighboring nodes to actually calculate its value accurately. And that node's value is going to go to infinity eventually if I keep reducing the size. So it's called a singularity. Now there's three things that can cause a singularity. A point load. Now I applied my load to an entire face, so we're not seeing it. But if I applied it to this corner only, we would see a giant red dot right there. Okay, so a point load creates a singularity. The most common time you're going to see that, though, is in an assembly with contact. Imagine two cylindrical faces colliding into each other. They're theoretically hitting at an infinitely small point. So that's going to create a point load, and you're going to see a singularity there. And that is going to oftentimes be the max, and it should be ignored. Singularities can be ignored because it's a local error only right in that region. So you can just typically ignore it. Another place is if I suppress this fillet. If I have a hard internal edge with no fillet on it, I'm going to get a singularity. And that's going to be my highest stress location. And that's going to be the max stress I see. That value, though, is false. Okay, really I need to leave in my internal fillets to avoid that singularity. Lastly, we fixed this top face. The edges of this face and the corners can get a really subtle singularity. Those typically are not going to come up as the max. They're really subtle, but they are there as well. So these singularities are nothing to be afraid of. All you need to know is leave your internal fillets and measure the important geometry. Do not look at the max value. So really what I need to do is set up some probes. Okay, when you have a plot up and you right-click it and go to probe, I can click on a node to look at the value there. All right, so I can set up a couple different probes in my area of interest. I can generate a quick plot to look at their results. We'll see that they're all in the neighborhood of 12.4, 13.3. And then I can save these as sensors for my convergence checking. Okay, now I'm ready to roll. Oh, I accidentally put my mesh control here. Okay, I should rerun this. My second run had 13.6. My default had 12. Okay, but now I'm going to do my second convergence check. So I duplicate the first one, call it number 2. And then I just reduce my mesh control. Again, maybe we put a better transition here, cut the value in half, and we'll hit OK and we'll rerun it. And now I went from 13.6 to 14.6 as my max. But again, I really need to be careful about this value in case it's a singularity. So really I want to right-click and probe and say from sensor, since I saved my sensor with this button. Okay, and then we'll plot that. Okay, so really we're looking at more of the 14 range here, something like that. Okay, I can even do it across geometry, so we could grab this edge or something like that and plot all the results across that edge. So again, the jitteriness here is, again, mesh error, really. It should, but I could kind of interpolate a curve through this. And again, we're looking at something, around 10.5 right here along this upper edge. Okay, but my max is in the middle. Here's a situation where a split line could be my friend. Maybe I throw a split line down the middle because I would like to look at results on the middle of the fillet instead of the top. All right, so it didn't change by much, but it was maybe 8% change or so, we'll say. So I got to keep going. I'll duplicate it one more time. Okay, we'll reduce our control. And we'll rerun it. Notice it's getting a little slower each time. Okay, now it went from 14.6 to 14.8. So a very small change now. So I've converged. Okay, so this is the point where I would stop. And now I would start doing my what if scenarios. You know, what if I made the fillet a little bigger and the wall thickness a little bit smaller, and then I would compare there. So now that I've converged, I can feel confident about these answers. You might do it one more time just to make sure you didn't run into some false convergence. Sometimes it's not necessarily this kind of exponential curve. Sometimes it might do a quick S curve. So you might do it one more time just to be double sure. And again, really I want to evaluate the whole problem to validate this. You know, checking for convergence is just one part of validating this test. Another part is making sure my material properties are accurate. Okay, I got to make sure these values are correct. Okay, if those are correct, then I got to look at my fixture. Okay, the fixture that I applied, is that correctly simulating real-life behavior, or do I need to model in the next set of components and bond them, something like that? Or do I need to try a different fixture? My load. You know, is my load accurately representing real life? Okay, I got to ask myself that to validate my test. Did I exceed yield? If you exceed yield, then the problem is not linear anymore. You might need to run a nonlinear study. Another thing that you might ask yourself is, did I see the large displacement message? That means your stiffness did not stay constant. Again, you need to make sure you didn't see that message. So if you kind of look over all of that and you give it the okay, then you can say your test has been validated and feel confident about that answer. So again, it takes a little bit of practice, but it's pretty easy to validate your test and converge you know, on the final solution. In this case, 14.8, which gives me a factor of safety of 2, a minimum 2. So if I'm looking for a factor of safety of 3, this design failed. But if a factor of safety of 2 is okay, then it passed. Just barely, but it passed. So that's checking for convergence manually. Now there's an automatic technique, and we'll look at that next. And there's two options there. There's an H adaptive, which pretty much does what we did, reduce element size. H stands for height. But it plays with every element independently, so it doesn't have to do it face by face. So it's very powerful, but it takes a while. You don't have as much control necessarily. So sometimes you'll do manual, sometimes you'll go with automatic. Another option is P-adaptive. This will help your elements map to the curved geometry better. So if you have a lot of bending occurring, twisting, or maybe a complex curvature to start with, you might do the P-adaptive instead. Notice the convergence graph though. It's converging a little bit slower than the H-adaptive in this situation, mainly because the part doesn't have that much curvature. It's a simple fillet. I typically go with the H-adaptive, at least at first, unless I know there's a lot of bending, twisting, and complex geometry. All right, so I'm going to I'm going to just do the H adaptive because the P adaptive you actually won't see much happen. If we go back to our default mesh and duplicate the problem, we'll call this H adaptive meshing. To turn it on, you just right-click your study and go to Properties. And it's on our Adaptive tab. So it's going to run the study, look at that energy norm error plot, figure out which elements need to be reduced in size, okay, and it'll reduce the size and rerun it. Okay, and it'll do several loops. You can tell it to do up to 5 at one time. Okay, now I could rerun it again if I'm not satisfied, but more often than not, it'll converge by 5. If it converges after 3, it'll stop early. Okay, it'll quit. Okay, you can give it a target accuracy, and we don't want to get hung up by one element not converging, because that would, again, we kind of want to look at globally the whole problem. So that's what this slider's for. Let's make sure pretty much every element is down to 1%. So we could get really strict with this problem because it's so simple, but on a more complex problem, you might need to loosen these. Okay, again, this one's really simple. It goes fast, so I'm going to leave it cranked up. Okay, and then you just hit run and watch it. Okay, check out the mesh after each run. You'll see the elements get smaller, but only in the areas of those quick stress gradients. All right, so it's doing loop number 4, and it stopped. So it did not need the 5th loop. It already reached our target accuracy. And notice what result we got, 14.8. It's the exact same one we got in the manual technique. And again, if I zoom in, I see that nice gradual transition. If we look at our error plot, notice the error, in our areas of interest is down to 1%. Okay, there's a handful, there's a few elements that are up near 5 or 6%, but still that's really not that bad. And notice it's around our area of our singularity, okay, again, the fixed edge. It's really subtle. It's not something I need to worry about, but again, it's nice to know that's what's going on. So this plot looks really good. Again, we've converged. We've gotten everything down to 5%. Most of it's down to 1% mesh error. Okay, last little tidbit, if you right-click results, you could pull up the convergence graph like you saw in my PowerPoints. Okay, I would probably, you could look at a lot of these at once, but if I look at one value at a time, I'll see the true values. So since stress is my concern, I'm going to look at the stress plot. And so we saw the stress kind of grow and then converge on the final answer. All right. Now on to the next problem, right? Drive shaft's not failing, but maybe our axle will. So we got another problem to analyze. But again, that's a good introduction on validating our simulation and controlling accuracy versus speed. So thanks again for joining our Tech Days webinar. I hope you enjoyed it. And that's it for me. Again, we'll get our recording up eventually. We'll also be sending out a questionnaire. If you could give us your feedback, we'd really appreciate it. And then in the future, we could make these better and better. So I think we'll also throw the link in there to the videos. If not, just shoot us an email. If you thought of any questions over the presentation, feel free to email us as well. You could email info@mcad.com, support@mcad.com, or my email, which is brendan@mcad.com. So thanks again for joining us, and have a good